In this presentation, we will discuss how to improve the design of database tables after the normalization process. Previously, the database designer normalized the data model to eliminate troublesome partial and transitive dependencies. The output of such a process is shown here as a set of normalized relations in third normal form. Remember that normalization cannot, by itself, be relied on to make good designs. Instead, normalization is valuable because it helps us eliminate undesirable data redundancies. Now the design shifts focus to improve the data model's ability to provide information and to enhance its operational capabilities. Therefore, as part of the data modeling activities, the designer must fine-tune the design to meet all transactions specified by the business rules, while at the same time maintaining data integrity and efficiency requirements. In the next few slides, you will learn briefly about the various types of issues you need to address to produce a good normalized set of relations. So what type of data issues should the designer look for as part of the data modeling process? Some of the most common issues are shown here. Check primary key assignments to ensure they meet primary key guidelines. Evaluate and enforce naming conventions. Refine attribute atomicity to ensure attributes are simple and single-valued. Identify new attributes as a result of transaction or data atomicity requirements. Identify new relationships to decompose many-to-many relationships or as a result of finding new data associations. Refine primary keys as required for data granularity, that is, the minimum level of data aggregation required by the data. Maintain historical transactional accuracy. And evaluate use of derived attributes when appropriate. Next, we'll discuss these issues in more detail. Also remember that any changes you make during any of these steps need to be propagated throughout the model. For example, if you change a primary key, you will need to change any foreign keys associated with this relation. First, you will need to evaluate primary key assignments and naming conventions. The designer must ensure the primary key meets primary key guidelines. The keys yield unique values, are non-intelligent, do not change over time, are security compliant, are preferably numeric, and preferably single attributes. In this example, the original job relation in 3NF had two attributes, job class and charge hour. However, job class is actually the job description. As you can see, the chosen PK has embedded semantic meaning. Also, this primary key could lend itself to data anomalies, such as entering database designer and DB designer for the same job. The solution is to add a new job code numeric attribute as a surrogate primary key. At the same time, you need to create a unique index on job description to ensure no duplicate jobs are created. In this case, job description is a candidate key and job code is the chosen primary key. To comply with naming standards, you also need to rename job class to job description and charge hour to job charge hour. Refine attribute atomicity and identifying new attributes. An atomic attribute is one that cannot be further subdivided. The original employee relation contained three attributes, empnum, empname, and job class. The empname attribute is not atomic, as it can be subdivided into additional attributes as required by the model for sorting or searching purposes. So in this case, empname should be subdivided into emplname, empfname, and empinitial. Furthermore, new attributes required for business purposes are identified. For example, in the case of the employee relation, it would be good to add the employee hire date attribute to keep track of the employee's years of service. Adding new entities and attributes, either by refining attribute atomicity or derived from business rules, may also yield new relations and relationships. One such case is shown here. The project relation originally had the attributes project number and project name. As you remember, the original report showed the project manager by placing an asterisk next to the employee's name. Therefore, you need to add the empnum attribute to the project relation as a foreign key to represent the project's manager. Refining primary key granularity and maintaining historical transaction accuracy. Granularity refers to the level of detail represented by the values stored in an attribute in a data row. Let's use the assignment relation as an example. In this case, the original relation had the project number, employee number, and assign hours attributes. The primary key is composed of project number and employee number. The assign hours attribute represents the hours worked by a given employee on a given project. However, what level of granularity does the assign hours represent? Is it an hourly total, weekly total, yearly, or project total? In this case, the designer needs to define what time frame the assign hours represents based on the business rules and requirements. After further refining, the assignment relation is updated to include new attributes. The new assign date attribute defines a daily granularity to each row in the relation. Therefore, the new primary key would be assign date, project number, and employee number. This new key guarantees a daily granularity for each row in the relation. Further, based on the business rules, it is later determined that the system needs to keep track of multiple daily hours worked by an employee in a project. Based on this new requirement, the new primary key would be assign number. This new surrogate key allows multiple hours worked entries for a given employee in a given project on a given date. The attribute assign charge per hour is added to the assignment relation in order to maintain the historical accuracy of the transaction. It would not be appropriate to assume that the charge per hour would remain the same for all time. That is, the hourly wage of any job is subject to change periodically. The job charge per hour attribute in the job relation represents the current wage of a job, and it is updated periodically every time that there is a wage change. Every time a new row is added to the assignment relation, the assign charge per hour uses the current wage of that time from the job relation. Evaluate the use of derived attributes. In this case, the assignment relation has a derived attribute stored in the actual relation. The assign charge attribute is the result of multiplying the assign hours and assign charge per hour attributes. This creates a transitive dependency. Assign hours and assign charge per hour determine assign charge. From the system functionality point of view, such derived attribute values can be calculated at runtime when they are needed to write reports or invoices. Storing the derived attribute in the relation makes it easy for application development purposes and saves processing cycles when writing aggregate reports. However, there are advantages and disadvantages to storing derived attributes in a relation. In this particular case, and for illustration purposes only, the designer chooses to store the attribute in the relation. The final normalized model is shown here. Notice the initial first normal form showing all the partial and transitive dependencies. The final model, including the design improvements, consists of the project, job, employee, and assignment relations. This concludes this presentation.